John Smart of Quality Steel had a problem. The oil lubricated gearboxes he was in charge of were failing. The gearboxes would operate fine for a while, but develop bearing vibration well before their expected lifetime. This caused the bearings to fail, leading to costly downtime and lost production. John's boss was very unhappy about the lost revenue and expected an immediate resolution. So John decided to pick up his phone and call the bearing company and get their advice. The bearing company asked John to send them one of his damaged bearings for failure analysis, which he immediately did. Upon arrival, the bearing company had its technicians inspect the bearing. After a close review and internal discussion, they called John back to tell him what they found. They told John the bearings were failing prematurely from wear caused by particulate contamination in his gearbox lubricating oil, and that their bearings required an ISO4406 Oil Cleanliness Code of 16-14-12 or better in order to maximize operational life and meet warranty. John was confused after hanging up because he had looked at a sample of his lubricating oil and it seemed clean. So John had many questions, starting with, what is ISO4406 Oil Cleanliness Code? How is it measured? And why is understanding that important to maintaining reliable lube and hydraulic equipment? John's problem stemmed from the fact that rotating equipment contained components such as gears and bearings, which require clean oil to remove friction between their sliding surfaces. What John didn't know was when magnified over 1,000 times, the lubrication gap between the sliding surface of the ball and the race of his bearing could be as small as 0.1 microns. How small is that? Well, the smallest particle the naked eye can see is only 40 microns, which is 4,000 times larger and approximately the diameter of a cross-section of human hair. That's why John couldn't see the tiny particles of contaminant floating in his oil sample, such as dust, dirt, silica, precipitates, and wear particles. He couldn't see as they were getting trapped and compressed under very high pressure between the sliding surfaces of his bearing, causing microabrasions and tiny cracks to form. He also couldn't see the chain reaction of wear as more and more particulate broke off, causing further cracks. And John also couldn't see as this erosion grew larger and larger, until the sliding surfaces of his bearings were no longer smooth, causing his bearing to vibrate violently. He did finally become aware after the vibration traveled all the way to his gears, causing them to eventually wear and fail. But by that time, it was too late to do anything. And all this started with particulate contamination so small, John would have required the aid of a microscope to see it. What John knew he needed was some type of early warning system for the cleanliness of his oil, similar to a pressure gauge on a pressure vessel, informing him in advance of an out-of-spec operating condition. However, instead of indicating pressure, this early warning system would tell John that his oil cleanliness had exceeded the required gearbox manufacturer's specification, thus allowing John to rectify the situation before his gearbox components failed prematurely. After researching online, John became aware that the reliability of his lube and hydraulic equipment increased exponentially the cleaner he kept his oil. So John began a program of sampling the oil from each of his lube and hydraulic systems regularly, and then sent them to an oil analysis lab for cleanliness evaluation. This lab uses a special piece of equipment called a particle counter, which has the ability to isolate the particulate contaminant in 1 milliliter of John's oil. This isolated particulate is then counted in total lots of greater than 4 microns, greater than 6 microns, and greater than 14 microns. Each of these counts are then compared to a universally agreed upon ISO cleanliness chart with specified minimum and maximum particles per milliliter ranges correlated to a specific ISO cleanliness number. For instance, in this example, the greater than 4 micron count of 71 particles per milliliter falls in the range between 40 and 80 and is therefore assigned the ISO code of 13. Correspondingly, the greater than 6 micron count of 39 falls between the range of 20 and 40 and is assigned the ISO code of 12. And finally, the greater than 14 micron count of 8 falls between the range of 5 and 10 and is therefore assigned the ISO code of 10. And it's these three numbers, arranged from the greater than 4 micron to greater than 14 micron, which constitute the oil's ISO4406 Cleanliness Code, with each progressive number indicating a doubling of contaminant from the previous. And it's this code which lube and hydraulic component manufacturers assign as recommended operational cleanliness levels for each of their components, such as, but not limited to, pumps, oil proportioning valves, and bearings. Once John was receiving his regular lab reports, and therefore had his early warning system in place, he was able to become more proactive by filtering his oil with his new MSC filtration technologies FilClean LHC filter cart on a regular basis, or whenever the oil was deemed out of specification. John's boss became very happy because plant productivity soared along with company profits. So John got a big raise, which he used to take his family to Disney World. Now, don't you just love happy endings?